Hi everyone, and welcome back to our AOA Month 8, where we'll be talking about binary search trees. So as a brief lesson overview, first we'll be talking about definitions, talking about some operations in binary search trees, what a balance factor is, how to balance using rotations, some examples of self-balancing trees such as AVL trees and red-black trees, and finally the applications of using these trees. Starting with the definition, a binary search tree, which we'll refer to as BST, is a data structure where each node in the tree has at most two children. So you can think of this as a literal tree with roots, where each root can only split off into two different roots. Specifically with binary search trees, in order to use the tree effectively, it must follow a series of rules. The first rule is that the left child must have a value less than the value of the node. So if you look at the example, let's start at the top. When you go to node, the first node, which is 8, you see everything on its left has a value lower than 8, while everything on its right has a value greater than 8. And every single node in the tree has to follow this pattern. The reason that this pattern is useful is because it makes searching for specific values very easy. For example, if we want to see if the tree contains the value 5, we'd start at 8, see that it's lower than 8, go left, see that it's bigger than 3, go right, see that it's lower than 6, go left. And since 5 isn't there, we can easily conclude that it is not in the tree.
Now let's go on to some operations that you can perform on a BST. The first one that comes to mind is just to create a tree. And after you create a tree, you can start inserting nodes into the tree. If you want to retrieve a specific value, you can also perform a search. And if you want to remove a node, you can also delete them. Finally, we have traversal. There are three main methods of traversal: in order, pre-order, and post-order. In the picture at the bottom right, you can see how each of these three orders visits the nodes. You can think of in order as going from left to right, pre-order as going from top to bottom, and post order going from bottom to top.
Moving,
Next,
sorry, yep.
next, let's move on to balance factor. So balanced binary trees have to meet two conditions. As the term implies, it's balanced. So what that means is that the difference in its height between the left and right subtrees is no more than 1. So that way, both sides of the trees have an roughly equal number of children. And then for each node, its left subtree and right subtree are both balanced trees. So that way, every single layer is more or less balanced. Balanced binary search trees are also known as height balanced, and we use this notation HB of k, where k is just a balance factor. A fully balanced tree is HB0, however, that's often quite rare. As long as it's within 1 or fewer, the tree is considered balanced. However, if the balance factor k is greater than 1, then the tree will perform rotations to self-balance. This matters because if our binary search tree gets really unbalanced, where one side of the tree has too many children, then searching for an element becomes um, log n time instead will become O of log n and O of n instead of O of log n. And we want to maximize efficiency in searching for an element.
So moving on to some rotations. Rotations are usually used, like as previously mentioned, when the binary trees are unbalanced. It's also specifically used in order to balance a tree when it's available, meaning that you can't use rotations all the time. So first, the two main types of rotations, and we'll look at examples in the following slide. First is a left rotation, where the operation is performed on a node to basically swap around a tree that goes to the left two times, where the node all the way on the left becomes the left child of the former right child, and the right child's left subtree becomes the new right subtree of the node. And the right rotation follows basically the exact same pattern just for the right. So that might seem a little abstract and confusing, so let's go look at some examples. So, for example, looking at the topmost example on the left, we have 42, 16, and 8. Notice this is technically following the rules of our binary tree, as in each child that's to the left of 42 is lower than 42, except it's not the most efficient way to balance it because there's a two-layer difference instead of a one-layer difference. So an easy way to correct this would be using a right rotation, where we twist it kind of in order to make 42 the right child of 16 instead of the parent node. In this way, we only get a balance or difference of 1. Similarly, looking at the left rotation, it works exactly the same way, except when nodes are balanced differently. Now, notice this isn't following the same rules that we set forth earlier, where every single node has to be on the left of its parent. It's because this is not following the binary search tree exactly as we specified earlier, but it's still an example of how you would do a left rotation. So, looking at the tree on the right, you might want to perform a rotation when you have a difference that's greater than 1. So if you have a difference in height greater than 1 between the two different legs, it's always going to be possible to perform one of these operations. Specifically in this case, we can swap this around by making 2 the topmost node and having 1 and 3 extend to its right. In this way, we get a difference of less than 2, which is more ideal.
Let's look at an example of a self-balancing binary search tree, or in this case, an AVL tree. It's one of the most popular and intuitive self-balancing trees. The mechanism for balancing is pretty simple. All it does is it checks to see if a certain node is balanced. If it's not, for instance, if there are too many nodes on the left, or if it's like left skewed, a right rotation is performed and vice versa. This process just repeats itself until the tree is considered balanced. And for instance, if it's a left-left case where the node that's unbalanced is to the left of the grandparent and also to the left of the parent, a right rotation is performed to balance the tree. However, if we have left right or right left, we try to convert them into left left or right right cases in order to do the balancing. The next example of a self-balancing tree that we'll look into is a red-black tree. As the name implies, all of the nodes are colored red or black, and they follow 5 rules. Rule number 1 is that the root or the highest level node is black, and every leaf or just a child that has no value is also black. Children of a red node have to be black. All leaves have to have the same black depth, and every simple path from a given from the root to any given descendant has the same number of black nodes. And once we have all of these rules and balancing rules, it seems a little bit more complicated than an AVL tree. However, it's more useful because fewer rotations are needed. So if you're trying to insert a lot of objects into your tree, it'll be more efficient in the long run. Now, if a red-black tree is unbalanced, there are many different cases to how it resolves such an imbalance. So if the uncle or a node that is on the same level as its parent is red, the child changes to the color of the parent, and the uncle is changed to black, and that the grandparent is changed to red if it's not the root. If the grandparent is the root, then it stays as black. However, if the uncle is black, then it works somewhat similarly to an AVL tree, where if we have the left-left case, we rotate the grandparent to the right and swap the colors of the grandparent and parent. If it's the right-right case, we rotate the grandparent to the left and swap the colors of the grandparents and parents. And then if we have a right-left or left-right case, we rotate the parent to the right, and then we apply the right-right and left-left cases respectively.
Moving on to some applications of binary search trees. So some that we've already talked about is searching and sorting numbers, which is especially useful if you want to determine whether or not a number is contained within a certain tree. Second is dictionary implementations, because in a dictionary, every single word comes before or after another word depending on its order in the alphabet. Therefore, we can easily use a binary search tree in order to depict this relationship. Third is going to be symbol tables, where we can use binary search trees to place symbols in order for easier indexing. Fourth is Huffman coding, which we talked about last month, where we can use binary search trees as a way to organize letters in order to compress the data into various definitions or codes of 0 and 1 in order to reduce the size. Next is database indexing, where we can use binary search trees in order to give a number to every single entry in a database, and we can sort those entries based on one specific property of that data. For example, if you wanted to sort a bunch of people, you could collect their phone numbers and sort that way. Finally is range queries, where data tree makes it really simple if you want to find every single thing within a simple range, as you can easily just look to the left or right of given trees in order to determine that range exactly. And finally is game development, where it's really simple to use binary trees as a sort of either dialogue path or simple AI for your enemies to follow in order to make game development more simple. So thank you, and this has been month 8 of AOA.